Okay, welcome back everyone. We're going to continue our study of DC circuits by looking at RC circuits. So an RC circuit is where we're adding a capacitor to a circuit that already has a battery and a resistor. So here's an example of a diagram. We have a battery or voltage source, and we have the same symbol as for our EMF. So it's a little bit small, but it looks kind of like this. That's our voltage. We have a switch, then we have a capacitor and a resistor. And we're going to be talking a lot about time with RC circuits, because what's going to happen is that this capacitor is going to begin with no charge on it, and it's going to fill up with charge. As we open the switch, charge will flow through the resistor and then onto the capacitor. So this is an important consideration, and much of the math that we do will be thinking about the time that it takes for everything to occur. And we're going to start by looking at this conceptually, and then we'll bring in some math. So we're going to start with the uncharged capacitor, and when you close, so here it is, the switch is open. This is where t is equal to 0. And then we're going to close the switch. So we have the direction of current, and we have our resistor and our capacitor. So the charge increases over time while the current decreases. And this is a very important idea to understand. Why is the charge on the capacitor increasing? Well, when we close the switch, positive charge is going to move through the circuit, through the resistor, and pile up on the left side of that capacitor. Likewise, negative charge will pile up on the right side. But as charge is piling up, it's harder to move more positive charge away from the battery and onto the capacitor. And that's because you're trying to cram together like charges. So conceptually, here's what it looks like when we graph charge versus time. Now you're going to notice that we're not writing charge as big Q, it's little q as a function of time because it's changing. And you might also have noticed in the last couple of videos that a couple of times I've written the current as a lowercase I. And that's because it is also changing. It's a function of t. So our goal in the next couple of minutes is to try to come up with an equation that describes this. But what you can see is that conceptually, the charge is going to increase from 0 to a positive value, QF. And there's a very important constant here, RC, which tells us a lot about how quickly the capacitor charges up. Likewise, we're going to have a starting current, I0, which is going to slowly decrease exponentially. And again, RC will give us a lot of information about this. Okay, so let's think about what happens in an RC circuit. So we have this time constant, tau, that we're talking about, which really tells us how quickly we're charging up here. And it actually increases with resistance. So that makes sense because as the resistance is greater, we're going to have less current. And so that's going to increase the amount of time to charge up. So larger resistors decrease that current. Okay? And less charge per unit time is going to arrive at the capacitor. So it takes longer to fill up. Also, tau increases with capacitance. Larger capacitors have more capacity, so they take longer to fill up. Makes sense? Okay, so one more thing about charging is that this time constant tau, which is equal to RC, and in one time constant, the current drops to 1 over E, that's the exponential base, 2.72, etc. Okay, so that's e to the 1. And in one time constant, the current drops to 1 over E of its initial value. So you can see that here. And the charge goes to about 64% of that. So basically 1 minus 1 over E. Okay, So now let's talk about how we get the equation for the charge on a capacitor as a function of time. So here is, here's our diagram when we're charging the capacitor. Okay, so we want to write things in terms of potential or voltage drops, and for the resistor, it's just going to be equal to IR. And we're just going to write that as VR, V resistor. You could also write it as I have it there as AB. Either one is okay. And then V capacitor, so that's V resistor. V capacitor, which is V from B to C. Unfortunate, the C is for capacitor and the other C is for point C. But that is Q over C. Okay, so this gives us the equation E in the battery, so we're going around counterclockwise here, minus IR in the resistor, minus Q over C is equal to 0. Current is a function of time, so I is equal to dq dt, and so we can write this as E minus, let's write it like this, R dq dt minus 1 over C times Q is equal to 0. Okay, now this equation looks a little bit intimidating. It's a linear differential equation, first order, and the thing is, we've seen this math before. Where have we seen it? Well, we did this with falling objects. So remember that we, a while back, showed that the speed of a falling object was a constant times 1 minus e to the minus bt over m. Okay, so let's do a little aside for a moment, and let's try to look at how falling objects are actually very similar to capacitors. Okay, so if we're falling with linear air resistance, we start with F net equals ma. And as we saw on the previous slide, we had the force of gravity going down, and we had a linear air resistance term. So force of gravity minus air resistance is equal to mass times acceleration. And acceleration we can write in differential form as dv dt. That's probably the biggest insight to take note of. And then we can rearrange things here, and we can write mg minus m dv dt minus bv is equal to 0. Okay, Q the capacitor. So the capacitor is charging from time t equal to 0. We're going to solve for the charge. So this is the loop rule, that the sum of the voltages in a loop is equal to 0. So we have the EMF from the battery minus IR minus Q over C is equal to 0. And as we did a moment ago, we rewrote the current as dq dt. So what we're going to do is we're not going to take the time to rederive the air resistance equation because that was done in a previous lecture, but we are going to solve this for Q of t. And so now what we need to do is to give us a little bit more space. We're going to get out of the PowerPoint and into OneNote for just a second. So here's our EMF, here's our resistor, here's our capacitor, and our equation was EMF minus R dq dt minus 1 over C Q equals 0. Okay, let's just check and make sure that that was right. Is that right? E minus R dq dt minus Q over C equals 0. Looks right. The first thing we're going to do is multiply through by the capacitance C. And we're going to see, that this is going to give us the time constant right here. There's RC, and there's dq dt. And then Q is going to be by itself. Okay? Next thing we're going to do in order to make this math a little bit easier is we are going to separate the derivative stuff from the non-derivative stuff. Okay? And if I wanted to, I could write this as 1 over RC times EC minus Q equals dq dt. Okay, now this is our differentiable equation. Okay, this is our diff EQ, I should say. And we want to separate the dq and the dt so that we can integrate each side. So basically we're going to have 1 over RC dt is equal to 1 over EC minus Q dq. Then what we're going to do is we will integrate from 0 to some later time t, and to make math teachers happy we could call that variable actually dt prime. Likewise, that could be q prime, and we will integrate from 0 to q. Alright, so this q right here is actually what we're gunning for. That's going to be our q as a function of time. Alright, the left side is very easy. We just get t over rc when we integrate that. The right side, we're going to have a natural log. We will have the natural log of EC minus Q prime evaluated from 0 to Q. However, if we take the derivative of this function, we're going to get a negative sign, so we need to put one in there in order to take care of that. So again, the left side is very basic. T over RC is equal to negative natural log, and now I can substitute. I'll get EC minus Q over just EC. Okay. Now some people will write that as CE, and maybe that's a better way to do it, so I'll do that in the next step. But I'm going to multiply through by -1, and I'm going to exponentiate each side to get rid of that natural log. I'm also going to take this stuff and bring it over to the left and make it equal to e to the minus t over rc. So I'm going to have CE minus Q over CE is equal to e to the minus t over rc. So far, so good. We're going to multiply through by CE. So I get CE minus Q is equal to CE times e to the minus t over rc. Okay, and then I'm just going to swap these two terms, and I'm going to write the Q on the left side. So I will have Q is equal to CE, and then it's actually going to be 1 minus e to the minus t over rc, and pause and convince yourself that this is the case. And this is going to be my charge as a function of time. Okay, now sometimes you'll see this RC is equal to tau. So sometimes you'll see it as e to the negative t over tau. But with my handwriting, I can never trust that tau to not look like t. So I just leave it as RC. Okay? Now a couple things that you should note from this. First of all, remember that capacitance is charge over voltage, which means that voltage times capacitance is equal to charge. And so what's this voltage times capacitance? Well, that is equal to Q final, the total, or we could even say the maximum amount of charge which appears on the capacitor. So now let's head back to our PowerPoint to finish this up. Okay, I have to advance a little bit. And when we solved this, we have a couple of very important boundary conditions to take into account. Okay, we came up with Q is equal to CE 1 minus e to the minus t over rc. And remember that we said that the starting charge on the capacitor is 0. And if you plug in 0 into this equation here, you're going to get Q naught is equal to CE times 1 minus 1. So the starting charge on the capacitor is 0. So that equation checks out. And then Q is equal to Q max, which we said was equal to CE when time goes to infinity. So e to the negative t, so as t goes to infinity, e to the negative t over RC goes to 0, and Q is equal to CE, which is what we said was Q max. So anytime you come up with a derivation like this, you want to see if it makes sense. Okay? Finally, actually, let's go to the next slide, because that's got our general solution there. Okay? So we already showed that Q as a function of time was equal to 0 when t is 0. We said that the Q max is equal to CE, and this is as t goes to infinity. But then also we can calculate the current as a function of time, which is dq dt. And so that's going to be Q max times the derivative of 1 minus the derivative of e to the minus t over RC, which is going to be minus 1 over RC e to the minus t over RC. So that's why this is the correct function for I as a function of time. Okay? And you also might recognize that Q max over capacitance is the EMF. So that means that the maximum current is when t is equal to 0, which is just E over R. So that's what I naught was in our equation of I versus time. So it just decreases like that. And as t goes to infinity, I goes to 0. So when the capacitor is full, the current drops to 0. Okay, so I think we have time to do one really quick example problem here. So charging a capacitor up. We're going to have a 10 mega ohm resistor connected in series with a 1 microfarad uncharged capacitor and a battery with an EMF of 12 volts. And what we want to do is a couple things. We want to find the time constant. We want to find the fraction of the final charge that's on the capacitor after 46 seconds. And we want to find the fraction of the initial current I naught that's flowing then. So we can calculate the time constant. We'll just call this parts A, B, and C. And the time constant, tau, is just equal to RC. So it's 10 mega ohms, 10 times 10 to the 6 ohms, times 1.0 microfarads, 1 times 10 to the minus 6 farads, and that's just 10. But here's the crazy thing. So the 10 to the 6, 10 to the minus 6 cancel out. What's the units of the time constant? Well, believe it or not, it's actually time. So 10 seconds is tau. Now remember, physically what tau is telling us is it's basically the amount of time to charge up 64% of the way, or to discharge about 2/3 of the way. Okay? So this time constant really does have units of seconds. And to dig into this, remember that resistance, ohms, is the same thing as voltage over current from Ohm's law. So volts over amps times farads. So that's ohms. And farads is going to be charge over volts. So that's coulombs. So this is all units that I'm doing up here. And that's the volts cancel, and I get coulombs per amps. But remember what an amp is. An amp is a measure of charge per second. So it's coulombs per second. And lo and behold, seconds is the unit of the time constant. That's just crazy. Okay, so what fraction of the final charge Q max is on the capacitor at 46 seconds? Well, we have that Q as a function of time is equal to Q max times 1 minus e to the negative t over RC. And so if you just leave Q max there, we don't care what it is, but you plug in 1 minus e to the negative 46 over 10, you're going to get about 0.99 Q max. And this makes sense because if you remember Q versus T, we make it up to about 2/3 of the way after one value of tau. Okay, so after 4.5 taus, we're going to be really close to full. Finally, what fraction of current is flowing then? Well, we can also guess that after 4.5 time constants, we're going to have basically zero current. And we can see that if we plug into this, I naught we don't really care about, but again, e to the minus 46 over 10 is going to give us about 1% of I naught. And I've rounded a little bit, but you get the idea. Okay, so that was a little bit long, but that kind of covers what the deal is for charging in RC circuits. So in our next and final segment, we're going to be talking about discharging in RC circuits. So we will see you then.